in the homework assignment, we have a projectile that is fired at the initial speed of so and so meters per second. In my example, it was 510 meters per second at an angle of elevation of 30 degrees. I think Brittany lost connection. Oh, okay. I heard that frog. What kind of noise a frog is making? Croaking. Yeah, it sounds like a frog croaking. So you have a projectile is fired at an angle of 30 degrees with initial velocity, and the thing with ballistic motion is you have the initial velocity, and there is, other than gravity, nothing else, no other forces or no other component play. So if we disregard friction, and most of you took this, studied this in physics, we disregard the friction caused by the air, that also slow down the velocity, and assume that, yeah, nothing is resisting, but the gravity is pulling down the projectile. So you have some kind of, turn out it's a parabolic motion, and eventually the gravity will win over, and the projectile is going to hit the ground. All right? And our task in this case is to figure out the range and the maximum height and the speed at the impact. All this was very important for artillery gunners, and this theory was developed mostly during the Napoleonic regime, where Napoleon at that time, of course, had the strongest army, and there was a push toward development of engineering that was both harnessed to enhance his military capability as well as a non-military. Hence the term civil engineering came to play to distinguish between an engineering that the effort designed to improve the military. But artillery was a major component, and the French and later on the Prussian studied very diligently and developed. Well, initially it was developed by Newton, but they were expert in calculating these sorts of things. But even in modern time, if you of course now those guns have computers to calculate these things, but you want to know, you want to measure, to include the wind, the air temperature, the humidity, all those little factors that contribute to resistance and change the projection of the missile. All right, so that was kind of long introduction to this problem. So I'm going to start. I don't know if I'll finish this problem. I'll probably do one part of it. So here goes. This will be homework 13.4, problem number 10. And it goes like this. So a projectile is fired at an initial velocity or with an initial velocity of 510 meters per second. At an angle of elevation of 30 degrees. From a position that is that's high position, 190 meters above ground. Okay, what we need to do, I'll do, as I said, I'll do only the first part. We need to find the range of the projectile. Those of you who serve in the military know that normally it's the other way around. You have a forward observer that gives you the range to the target, and as gunner you need to calculate well, the direction, of course, what the forward observer will give you, but you need to calculate the angle of elevation such that the projectile will hit the target at the prescribed range. Stephen, you went recently through military training. Did you do any of this sort?
No, not artillery.
Not artillery. Okay. And again, in modern days, it's when you I think in modern time, only when you fire a mortar, which is really a very basic rudimentary artillery piece, you kind of set the angle of elevation by hand. Everything else is now computerized. Anyway, so how are we going to approach this problem? Well, what is it that we know? We know that the only component for the acceleration is the gravity, and the gravity has only j direction. So if you want to write the gravity in terms of the acceleration in terms of ijk, then it will be gj, where g equals 9.8 meter per second squared. Okay. The velocity now, how we interpret the initial velocity? Well, the initial velocity has a j. It depends how you set up your coordinate system, but if you set up the coordinate system such that I will be the horizontal, j will be the vertical, and k will be the third dimension, which really doesn't play any role in this case, then so we can reduce it to 2 dimension and say that we are looking at a system like this, simply I and j direction, or x and y direction. Okay, so if you have 30 degrees and this is the initial velocity vector, then you do have a horizontal component. So in the I direction, if you look at the initial velocity, v sub 0, it has 510 meter per second, and this should be the cosine of 30 degrees in the I direction, plus the 510 meter per second sine 30 degrees in the j direction, as that will be the vertical component. And we translate it, cosine of 30 square root of 3 over 2, so you have 255 square root of 3 in the I direction, and sine of 30 degrees is 1/2, so 2 plus 255 in the j direction. Okay. All right. Well, I kind of went ahead and defined the initial velocity because the velocity vector is, of course, the integral of the acceleration. And since we have only one component, then, and by the way, this will be negative because the gravity pulled down. So let's not forget that it's negative 9.8. Okay? So it's negative g. So we have the integral of negative 9.8 j dt, or simply negative 9.8 t plus c1, like we had before. Now, what is c1? Well, we look at the vertical of the initial condition v sub 0, and this is what we had here. So notice that the initial condition has nothing to do with well, from here the t disappeared, and we have simply c1, the constant vector, and this has to equal to what we wrote here, 255 square root of 3i plus 255j. Okay, and now we include this in our result. So the vector, the velocity vector, now we modify and we we didn't have, I'm sorry, I didn't put the j here, but it's still a vector, so negative 9.8 tj plus c1, and now when we add the c1 component, then we have the horizontal component 255 square root of 3t in the I direction, and in the j direction we have the 255 minus 9.8 t j. And we for the position, now we're going to continue, and the position of course is the integral of the velocity. So we need to integrate this, and as we integrate these two components, then we have 255 square root of 3 divided by 2 t squared in the I direction plus 255t minus 9.8 over 2, so we'll write it as 4.9, as we know how to divide by 2, at least part of the day. So, like so, t squared, and this will be in the j direction plus c2, another constant vector. So now, what is the constant vector? We are told that the position is 190 meter above the ground. So at r of 0, the initial, we know that everything here, well, let's write, we have it's 190 meters in the j direction, upward, or above ground. And this equals to, let's see what we lose here. We lose the I and the j component, so we have simply C2. So again, the constant vector C2 is just 190j. And now we can finish this up, and the range, well, I didn't write what we need to find. Find the projectile, but I didn't say what. Projectile maximum range. Nobody noticed that this omission? All right.
You said find the range of the projectile, but you didn't write it down.
Oh, range of the projectile. Well, the maximum range. Oh, the range of the projectile. Right. So thank you, Brittany. No, see, because we need to replace, we need to find what is the vector constant C sub C1. Yeah. No, this is the data that we are given. If you remember, well, I didn't say it in this class. In order to substitute the constant of integration, you need to know something about the outcome of the integral. That's what we call either initial position or other data. For instance, if we didn't know the position at time t equals 0, then maybe we should have known something about the velocity at time t equals 4. But normally we know the initial condition. We don't know what happened down the road. But we can use this information to replace the constant of integration. This is called the initial condition problem. Okay? Go ahead. Guide me. Are we on the right column or left column? First line. V of t, 255 square root of 3 ti. I'm sorry? Yeah, you have the t here. V of 0? Yeah, because this is the initial velocity. This is what we calculated here. It's not, there is no t. It's at time 0. That's the initial velocity. That's the muzzle velocity, what we call it. There is no t in it.
So in V sub
It's
t, you added a t into it.
Right, because then it became a function of time.
because I now substitute.
But if the t was 0, then that would be no longer in.
Ah, okay. The reason, yes, good point. Good point. So, in the I direction, we have 255 square root of 3 without the t, and then 255 plus, yes. So, thank you. Who was that? Cameron who picked up? I'm sorry? So now when we integrate, then we don't have the 2 here, we have just the t. So we need to make some adjustment here. So it will be 255 square root of 3t. All right. I think the rest is okay. Now going back and including the initial position, 190J, so the position going to be 255 square root of 3t in the I direction, and in the J direction we have to include the 190, so we have 190 plus 255t minus 4.9 t squared in the J direction, and this will be the position vector. Notice that the J direction give you Galileo formula. If you remember, Galileo formula deal with the vertical component, treat it as almost as a free fall. Initial position, no, actually free fall with initial velocity. Initial position 190. Initial velocity time multiplied by the time, and 1/2 gt squared, if you recall Galileo formula. So the J component is Galileo formula. So let's write here a note. The J component is Galileo formula for vertical motion. Without the middle term, it will be simply free fall. Okay, where you have y equals y sub 0 plus v sub 0 t minus 1/2 gt squared. That's Galileo formula, where y sub 0 and v sub 0 are initial position and initial velocity. Notice that y is positive, so upward, and what caused the fall down is the acceleration component, 1/2 gt squared, which is stronger. So this was a side note, and now we want to find the range. How we find the range? Well, the range is the horizontal component, distance, but to find it we need to know the value of t. How are we going to find it? Right. When the projectile hit the ground, then that will terminate the flight. So we calculate the range by finding the time when the projectile hit the ground. So we need to solve 190 plus 255 t minus 4.9 t squared equals 0. Okay? And then we find let's say t equals some value of t like so, okay, and then the range is the I component we'll write simply the range is 255 square root of 3 times t, that particular value that we found by the calculation. And this concludes this particular example.